Nate. I'm really excited for RubyConf Mini and thrilled to be a part of it. My name is John Hawthorn. I use he, him pronouns. I'm on the Ruby core team, the Rails core team, and I'm a staff software engineer on the Ruby architecture team at GitHub. Largely, I like working on performance and things like that. Online, you can find me at jhawthorn in most places, like GitHub, Twitter if it's still online. So also, I've been enjoying the ruby.social Mastodon, so that's worth checking out if you haven't already. This talks about the is_a method, which you can call in any object, and it tells you whether or not this object is of this class or module. I think the technical term they usually use is whether it implements this class or module, but I just, basically it checks if it's an exact match or also the inheritance chain. So a few quick examples just so we're on the same page. The string foo, is it a string? Yes. Is an integer? No, it's not. Yeah.
Okay, there we go. 1, 2, 3 is an integer. Yes, that's true, but it's also a numeric because is_a checks the class ancestry, and integer is a subclass of numeric. So I know these examples seem ridiculous, kind of like this outdated meme where the guy asks whether a butterfly's a pigeon, or maybe this would be the Ruby version. And I think that's actually really accurate. As like people, it's really intuitive when a class is part of another class, so it's weird that it would be something that could be slow or we'd have to make fast, but Ruby, like a Ruby VM needs to have, like any computer, a strict definition for how you figure those things out. I also learned when researching this that this character is actually an Android, so apparently it's like really applicable. So it's not just is_a, that's just the one I was easiest pronouncing because I don't know what, I call the one on the bottom triple equals, but I wasn't sure about that. I've also heard threequels or case equality, all of which are good. So other methods that do vaguely the same thing or exactly the same thing, kind of is just an alias. Triple equals, same thing, but reverses the arguments. Case statements actually just call triple equals, as do rescue statements. So if you want, you can override triple equals on a module and have dynamic behavior for rescues. You probably should not do that, but you can. And protected methods are the same. They do a class inheritance check when you call them. So used all over the place. And probably because of that, I found repeatedly that these methods seem to be taking up about 2% of total Ruby runtime. That obviously varies by application, but it seemed like many of the things I was measuring, this was a constant. So to back that up, that was found via profiling. Profiling's really great and really valuable. If you're not profiling, you're just kind of guessing at what's slow, which is, I think, a popular thing to do on certain websites. But profiling's a good idea. So I normally use StackProf, which is a sampling Ruby profiler. RBSpy is also very excellent, whatever you prefer using. So we like to benchmark a lot with RailsBench, which is a benchmark of a very simple Rails app. Just has a couple endpoints, and you hit them. It hits them like randomly and thousands of times. And when we, if we run StackProf against that, it shows us that module triple equals takes 1.7% of runtime. And here's one I got from github.com in production where is_a was taking almost 4% of time, which is like wild, and this page wasn't typical, but it's just continually seemed like something that was slower than you'd think it would be. Because I'm not sure, I genuinely don't know if 2% is like a lot or a little, but I sort of use a rule of thumb that like if we spent 2% of time doing something useful like rendering HTML, I would just, that sounds great. But 2% of time doing like, is a pigeon a butterfly check, that doesn't sound quite right. So I'm not sure, I mean, I kind of trust the StackProf results, but some older versions had some, they were skewing results in some ways, so I thought it was good to also back this up by some C profiling. I like using Linux Perf. It's a really great tool. It's super fast. You can run it in production. It does have a very open source interface, which I know is rich. I just plugged my Mastodon, but it is really good. It's a TUI, so you can run it on the server. And measuring Rails bench, that showed me 2.4% of time calling inside RB objs kind of, and doing a profile of a load test type thing for the GitHub application showed similar results. So what is this RB objs kind of it was showing us? If you run Linux Perf, it's not a Ruby profiler like StackProf or RBSpy. It's I think of it as a C profiler, but it's really just a low-level profiler. So it tells you the C methods being executed, not the Ruby methods. And if we can guess, based on the name of RB objs kind of, that it's probably kind of, or is a, but we can also verify that by grepping the Ruby code base. And inside object.c, we'll find the definition of RB objs kind of, as well as it being defined as the implementation of kind of and is a on kernel. We'd also see it's used in a bunch of other places. We'd find to like the triple equals and the protected methods. So looking at that implementation, it basically just calls, it gets the class of the object and calls class search ancestor on it. And here's the implementation of that. And I'll just convert that to Ruby for ease of reading. So what it does is it gets a class and the class you're searching for. And then there's a loop, and on each iteration of the loop, it checks whether the class is equal to the class being searched for. If they are, it returns true. Otherwise, it looks up the superclass and continues the loop until it's out of ancestors, and that returns false. So it's going over a linked list structure, would look something like this. So first we check if a butterfly is a pigeon, then we check if an object's a pigeon, and then we check if a basic object's a pigeon, none of which are. But that's not totally true. I told a slight fib, which is that these also have to check not just the class ancestors, but also the module ancestors. And the way that's done in C Ruby is that it has these weird hidden iClass objects, which I actually, I don't know what it stands for, but I've always assumed internal class. And those represent the inclusion, or if you prepend a module into a class, you get one of these objects. And I think that's just a implementation detail. You're never supposed to see this from Ruby. It's hidden. It's just made it so the C Ruby code internally can treat it as if it's single inheritance, even though it has this kind of multi-inheritance mix-in magic. So you're never supposed to get access to these from Ruby, but there's actually a debugging API that lets you get these internal things. I would say never use this in real code, but I do recommend opening up a IRB session and trying it out on some classes that have something included into them. I found it very helpful when making this, but they are a debugging interface in C Ruby only and might go away at any time. So this is more the real implementation. We're looping over these objects, and we're checking not just the classes, but also the iClasses. So, that's still maybe only 5 items in a linked list to check. That doesn't sound too bad, but there's a few things about this being a linked list that tend to hurt performance. Linked lists, like modern CPUs, really want the data they're operating on tightly packed together, contiguous, all within cache lines, so that they can do pipelining and better branch prediction and fancy things like that. But because these are split up into separate objects, the CPU sort of struggles with it. So just consider these 5 comparisons more expensive than usual, just because the memory layout happens to be awkward. And in a lot of cases, it's not just 5 comparisons we have to do. So this is the number of ancestors we end up with in GitHub's largest application. Object if you just open up IRB, object has 5 ancestors, including itself, but in our application it has 11. And built-in classes like hash, array, and string have 20. And that's because a feature of Ruby is that you can include or prepend onto the built-in classes. It's sort of we can argue if that's a good or bad feature. I think it's good. I think it's a part of Ruby's popularity that you can add hash symbolized keys and things like that. And our application actually gets very large. Our largest active record model has 305 ancestors. And you could think that maybe our application's kind of messed up, but I actually think this is evidence of good engineering. We've tried to split things into modules that have more reusable or testable interfaces. So I think it's a good thing. And I don't think it's necessarily a problem. So what can we do about the performance problems of this? We could improve the implementation of ISA. We could simplify the class hierarchy, but as I said, I'm not too keen on that because I'm not sure. I think it can be evidence of good engineering, and it also seems like something that won't stay fixed. It's very likely at some point we'll include more libraries that do the same tricks, and we'll have the same performance problem again. We could avoid calling ISA, try to replace some of the hot paths that are calling it with instance of, which doesn't check class hierarchy. I'm not too sure about that either as an option. It just seems error prone, and I kind of like believing the author of code. If you wrote code a certain way, it would be nice if it was able to run as intended and there wasn't a linter that was double checking your intentions. You could also use respond to. This is often a recommendation so that we can do duck typing instead of class checks. So maybe instead of checking if the object you get's an array, you check if it responds to each. I think that's not bad advice on a case-by-case basis, but again, I'd rather trust the developer writing code that maybe they knew what they wanted. And again, this is case statements and things, so pretty core to the language. And when we're talking about where to fix things, it's obviously easier to change things in the application, but I always want to think about trying to change things in the library, framework, or language, just because you get a more broad and more complete fix that way. It's likely to stay fixed longer, and you fix it all across your application rather than in just the small areas that might get rewritten. So let's fix it in CRuby. And to start, after seeing that this was a problem, I had no idea on how to do that. So an exercise I often use when wanting to implement something inside of the CRuby VM is I'll try to write what I want to do in Ruby and then convert it. So one option, anytime I'm writing code in Ruby that's looping over an array and that ends up slow, I try to use a hash. So try that here. Make a hash, put all the ancestors of pigeon in it, and then to check if the pigeon is a butterfly, we just do hash.include on it. Of course, we can't have just a static table, so we need to build it dynamically. Just do the same loop we were doing before, but now instead we add it to a hash, and then we have to cache that somewhere, and we'd probably have to have some sort of invalidation to get rid of it if something new is included or prepended, because again, you could do that at any time in Ruby. So implement that, or took that Ruby, it's pretty much the exact same in C. This is often the case. C Ruby is written in C, so anything you can do in Ruby, there's generally a way to do it more or less the same in C. I might have put my finger on the scale a little here in that I wrote very C-like Ruby to begin with, but generally I find this a pretty good approach to getting things working, and then can iterate from there. So I implemented this. I wrote a benchmark to test it where I created classes with progressively more and more ancestors, and then tested ISA against it, and this is the result I got. So initially, looks pretty good. Ruby 3.1 is the line that's trending way upward, and this hash lookup stays totally stable regardless of how many ancestors you have. So that seems really great. But if we zoom way in for low numbers of ancestors, which probably also would include when you get a match, like if you actually ask if a butterfly is a butterfly, you get, you have to do fewer loops with the previous implementation, whereas in the new implementation, you always have to do a hash lookup. And a hash lookup is kind of complex. It's not, horrendously complex, but it's a lot slower than, doing a few loops in memory. It has to do, I don't know, whatever hash tables do, which is multiply by prime numbers or something. And also, this is going to use lots of memory, and we need to do that cache invalidation that I didn't want to do. So there might have been a way to sort of pick a cutoff point and switch between the two approaches, but this didn't seem the right way to go. And going in, I think I knew that, but seeing that flatline graph was really helpful in knowing that a better approach was a good idea here. So for my second attempt, I wanted to find something with a different trade-off. One thing I was thinking about is that it seemed like most of that depth came from those modules that were being included from the I classes, and I wasn't too sure that those were actually important. Like, if we're not calling ISA with modules very often, we're just wasting time scanning through them. So I added some instrumentation to audit the calls to ISA, which is a performance review season way to say I added a print statement. Worked very well. So I added a print statement, did some shell scripting to figure out who we were calling the most, and it turns out we almost never call ISA with a module. It's really rare to do. So we can probably just, we still have to implement that, but we don't need it to be fast. So I figured, let's try making a second linked list on top of the first one. So now instead of, we have two lists, one goes through the things normally, and the second gets to skip over the I classes when we see them. I like this approach. It's fairly simple. It turns out there's no cache invalidation because you can't change the superclass of a class after it's defined. So you can do this on the class boot and it'll never change. I added some, I wasn't super sure about this, so I added some more instrumentation to check. It still loops, it's still big O(n), it's still a linked list, but I think this wasn't a bad idea. But and probably if there wasn't a better solution, I would have been happy to propose this and try to ship it. But I kept looking just because having a linked list bugged me. So next I thought, well, I've tried a hash, I've tried a linked list twice, maybe just try an array. So I took the objects, and rather than being a linked list, I kind of like making the hash table, but I just made an array instead, and then did a linear scan through that array, and turns out it was much faster than Ruby 3.1. Of course, it's no longer totally linear. It now grows a little bit as we gain more and more ancestors, but it's way faster than the linked list approach, which is validating because of the assumptions that the linked list was a bad thing. And when we zoom way in, I think this shows it being slightly slower. I think that's because I didn't actually do the cashless approach, because I was building the array lazily because I'm lazy and I didn't end up shipping this. But I think it would be safe to assume that it would have equivalent performance for low numbers of things, if not better. But this still had the problem that it grew with the size of the modules, and keeping in mind that GitHub has classes with 300 ancestors. So I figured maybe we can apply approach 2 and approach 3 together. So we could just take the array we had and just get rid of the modules. And once I did this, I noticed an interesting pattern. So here's, I'm switching examples a bit. So this is whether a type error is an exception. So we could just scan through this array, check whether each thing consecutively is an exception. We would have returned true here, but if we hadn't, we'd keep searching. And one thing I noticed once I was building these tables of the superclasses for each object is that they kind of line up. Which makes sense. The superclasses can't change, so once you inherit something, it's going to share, and once there is a match, it's going to share common ancestors after that point. So we actually don't need to compare exception to object or basic object, because we know that it has two superclasses, so we'd never need to check the last two things of the other class. And not only do we not need to check the last two things, we don't need to check anything except for that like second or third to last thing for a match. Anytime we have a class which inherits from exception, it's going to match in that exact location in the built array with a single comparison. So just a few examples to prove this to ourselves. It's what I needed. So exception matches exception. It doesn't match hash. If it did inherit hash, hash would be in exactly that location. It doesn't match integer either, obviously, and we have to check integer in a different location because it has an extra superclass. Doesn't match integer, but if we check standard error, which type error is a class of, it does match, even though we're checking a different location. And of course, it's an object, like most things. So I was thrilled to find this because it matched my sort of mental model for how easy it is to tell if a pigeon is a butterfly or vice versa. And it turns out that this is a fairly somewhat known technique. The JVM does it, and I think Truffle Ruby also has something like this. And the implementation is very nice and simple. So we just get a depth and we do a single comparison, and that's it. So that gives us constant time, no loops, and no cache invalidation. So all the things we were looking for. There was a slight downside, which is that it does use more memory. We need to build this array for each class in order to check it, and I really wanted to build the array at boot time rather than building it lazily, just so it's even faster. Again, our application is very large. It has 92,000 classes, which I don't know if that's the largest. I'd love to know. Please tell me if you have more classes than that. A lot of them are weird. They're like anonymous and singletons and things like that. So we don't have that many like files with classes in them. But it ends up using a lot of memory. It used 88 megabytes total, and making this change added 6.5 megabytes. So that might be worth it, but it's not ideal. One thing we found is that with a small tweak to this idea, we could save a lot of memory, which is that so the arrays were all unique because they have like the self class at the top of them. But if we remove that from the array, they end up largely, or there's a lot of duplication in them, especially this kind. It's really common to make errors based on standard error. This was like a huge number of classes in the system. And so if we do this, and we build some way to deduplicate them, we can end up sharing the same memory for this array. We just have to make sure it's safe and freed altogether. So did all that, and that ended up saving most of the memory used. So now it's just a 1 megabyte increase, which on top of 88 megabytes is nothing. So here's our adjusted implementation. Start with this check. We just need to add an extra return true if class matches the search, because the self class is no longer in that superclass array, so we just need to add an extra check for it. And of course, going to convert this to C, we need to do a bounds check manually, because Ruby will do it for us, but C won't. So cheating a little here. And then once you do that, it does convert very neatly just into C. So I implemented this, ran the benchmark, and it's this line at the bottom. It's faster than everything we've done before because it's a single comparison. And even zooming way in, it's always faster. So this is what's going to ship with Ruby 3.2. Next time you call ISA or any of these methods, I hope you think about how they're implemented. I think it's very satisfying to know, and I like thinking about the way things work in the implementation. Maybe you'll try profiling your own application and consider contributing upstream to Ruby itself or a framework, or just letting the community know where you're seeing performance problems in your application. I think together we can make Ruby faster and the language we all hope it can be. Thanks.